Okay, so tonight we are going to use what we worked on in the last webinar to determine the sketching of a graph. So we'll use the local max, the local mins, concavity, and a few other things to sketch the function. We will also talk about antiderivatives and trigonometric antiderivatives, and we'll also do an example on optimization. Okay, so let's sketch the graph of the function x to the third minus 2x squared minus 15x plus 10 by finding local extrema and inflection points. So we're just basically going to find out everything that we can about this graph and put it all together and graph it. So one thing that we can start with is finding the local max, local minimums. So let's first start by finding the local max and minimums. And it's possible that we won't have a local max or a local min. We just have to see if we can find them. So let's take the first derivative. When we do, we get 3x squared minus 4x minus 15. So the first derivative, we're going to set that equal to 0 because that will tell us where the graph goes flat and changes directions. And that will give us a potential local max or local min. It could also end up being a point of inflection. We'll just have to use either the first derivative test or the second derivative test to make that decision. So to solve this, the easiest way to do it is to factor it. So the first term, 3x squared, can only be broken down into 3x and x. What I usually do is I usually bring down the first sign. And it's possible that we might have to switch this after, but I usually just bring down the first sign and then what's the second sign going to be? Good. I have a negative 15, so a negative times a positive would give us a negative. And factors of 15 that will give me a 4, a negative 4 in the middle. Well, 3 times 3 is 9, and then minus 5. But what happens here is if I multiply this out just to make sure that I end up with a negative 4 in the middle, I get 3x squared plus 9x minus 5x plus 15. Excuse me, minus 15. Sorry about that. So the problem is we end up getting a positive 4x in the middle and we need a negative 4x in the middle. So this is what I was saying earlier. In cases like this, all we have to do is just switch the signs and we'll end up in the right place. So now I have 3x plus 5, x minus 3, and that will give me a minus 9x. Just one second. That will give me a minus 9x and a plus 5x, which will get the negative 4x in the middle. So I know this is factored correctly. So let me go to the next page. I have 3x plus 5. And then x minus 3 equals 0. So 3x plus 5 equals 0, and x minus 3 equals 0. So one of my critical points is that x equals 3. And the other one, when I move the 5 over and divide out the 3, I get negative 5/3. So I have two critical values, negative 5/3 and 3. And now I need to check each one of these and determine if they're a local max or a local min, and that gives me an idea of basically how I'm going to graph this. In this case, I would use the second derivative test, and again, it's completely up to you, but taking the second derivative is fairly straightforward here because we have a polynomial. And also, if I'm going to find the inflection point, I need the second derivative anyway. So I'm going to have to figure out where the graph is concave up or down. So I might as well just take the second derivative now. And what is the second derivative? Well, the unfactored, good, 6x minus 4. So the second derivative is 6x minus 4. So I'm going to plug in both the critical points to the second derivative. And when I do that, I get 14 when I plug in f of 3. And when I plug in negative 5 over 3, I get negative 14. So remember, what we take out of this is that it's positive and that it's negative. And what does a positive second derivative mean? Very good. So positive second derivative means it's concave up, which means we have a local minimum. And negative second derivative means it's concave down, which means we have a maximum, a local maximum. So now I know that we have a local minimum and a local maximum. So our local minimum is at x equals 3, and our local maximum is at x equals negative 5 over 3. So remember, the critical value tells us where the x value, so where the local max and the local mins are happening. And one thing that'll be useful when we're going to sketch them is finding their corresponding y values. It'll just help us to calculate or to graph the function. So how can we find the corresponding y values? Very good. We can plug them into the original function. So that'll tell us what the y value is at each of these points. So at x equals 3, the y value is negative 26. So if I went back and plugged into the original function, I would get negative 26. And if I plug in f of negative 5 over 3, or plug in negative 5 over 3, I get a decimal here, which is okay because we're just trying to get a rough sketch of what the graph looks like. So I will just round it at 2 decimal places. Okay, so this is just giving us an idea, again, to help us figure out what the graph looks like. So now let's find the point of inflection. So remember, the point of inflection is where the graph changes from concave up to concave down. So concave up and concave down deal with the second derivative. So the point of inflection happens when the second derivative equals 0. It's basically a critical value, but it's finding out where, instead of where the local max or the local min happens, it finds out where the point of inflection is, or where the graph changes from concave up to concave down. So we can take the second derivative, which we found to be 6x minus 4, and set it equal to 0. So solving for x, we get x equals 4 over 6 or 2 over 3. Okay, and at x equals 2 over 3, it is also a good idea, again, to figure out what the y value is, just because it will help us to kind of plot these points. And I would do the same thing. I would plug this into the original function. And I get y equals negative 0.6. Are there any questions so far? Okay, so again, we're going to put all of this together into a graph, kind of using points. So I've got this point. I've got a local max and a local min. Is there anything else that could be pretty useful when trying to graph a function? Well, our original function is y equals x to the third minus 2x squared minus 15x plus 10. One other useful part of, well, a couple other useful pieces of information that we could use when graphing it is we could find the x and y intercepts. X and y intercepts can give us an idea of where the graph crosses, and that can help. The issue with finding the x-intercept here is we would need to factor this, and factoring it isn't going to be overly easy. So that won't be something that would be helpful now. If we could factor this easily and get the x and y intercepts, then that would be good to know. But we can get the y-intercept. Do we know anything about how to find the y-intercept? Good. The y-intercept is when x equals 0. If we think about when the graph crosses the y-axis, the x value is 0. So I have y equals 10, because all of the other terms zero out when x equals 0. So we have kind of another point to give us an idea of what the graph looks like. Okay, so putting all of this together, and again, I'm just going to get a rough sketch. We know that the y-intercept is 10 when x equals 0. So if I want to go ahead and just say that this is about 10. I also know that the local maximum happens at x equals negative 5 over 3, and the y value for that is 24.82 roughly. And again, I rounded that just because we ended up with a decimal. So I can go ahead and label about 25. I also know there's a local minimum at x equals 3 and y equals negative 26. So just trying to make this as close as I can. So that would be about negative 26. And then x equals 3. Again, just trying to roughly label. And negative 5 over 3 is about negative 1.67, rounded. So just to give me an estimate, so we have a local max at about 25. Then the graph is going to cross this x-axis. Actually, let me choose. So we have a local maximum here. It crosses the y-axis. And then we have a local minimum down here. So if we have a local maximum, just to the left of the critical value, is the graph increasing or decreasing? So just to the left of the critical value, when we have over here with this local maximum, just to the left, the graph would have to be increasing, because we would increase until we get to the local max where the graph goes flat, and then we start to decrease just to the right. We're going to cross the y-axis at 10, and then the graph keeps going until the local minimum of negative 26 at x equals 3 changes directions and then continues. So that's a rough sketch of what this graph would look like. We also found the inflection point which was at x equals 2/3. So at about x equals 2/3 and then y equals negative 0.6, just going to confirm that this makes sense with the graph that we have. So the point of inflection is where the graph changes from concave up to concave down. So that says that at about here, the graph changes from concave down to concave up, which looks about right. About negative 0.6, probably a little closer to the x-axis than what I've drawn, but that's the y value of negative 0.6, and about y equals 2/3. That's where the graph changes from being concave down to concave up. So this is a rough sketch of what this graph would look like without graphing it in a calculator. Okay, so I basically wrote down anything that I could find useful. So in this case, the local maximums and minimums we found, and then we also found the y values that correspond to those, because that way we could get an idea of how tall or how high up the graph goes or how low the graph goes. Yes, so you're correct. So if we had a second derivative that equals 0 everywhere, that means that the first derivative would have had to have been linear. Or excuse me, the original function would have had to have been linear, which means there is no local max or local min. You are correct. No problem. Okay, so this is a rough sketch of the graph. Let's go to another example where we have a rectangular plot of farmland that's going to be bounded on one side by a river and on the other 3 sides by a single strand electric fence. And we have 2,800 meters of wire for this fence. What is the largest area that we can enclose, and what are the dimensions? So what I usually do in cases like this is I try to draw a picture just to give an idea of what we're looking at. So we have this river on one side, and then we have a rectangular fence. So let's just label a few things. So let me say that this is the width of the fence and that these two are lengths. You could label them with x's and y's or any other variables if you want. So what information can we have? What do we have here? We know we have 2,800 meters of wire. What would that represent? Another question is, we're trying to find the largest area. How would we find the area of this rectangle? So we have a couple different equations that we're going to be working with. What would be the area that's enclosed by this? Oh, good. Great, so the area that's enclosed, and then we can also find the perimeter, and the perimeter is 2L plus W. And typically the perimeter of a rectangle is 2L plus 2W, but in this case we have one side that's the river, so we don't have that extra W. So that's the perimeter. Do we know anything about a value for the perimeter? Good. We were told that we have 2,800 meters of wire, and assuming we want to use all of it, we know that that 2,800 will equal 2L plus W. But we are trying to find the largest area we can enclose. What is the area of that rectangle, this field? Very good. Length times width. So the area is what we are trying to maximize. Which basically means I want us to find the max, the local maximum, is really what I want us to do. The problem currently is we have two variables here, length and width. So, because to find the local maximum, I would take the first derivative and I'd set it equal to 0, but I have two variables. Is there any way that I can only have one variable? Well, that's where the perimeter comes in. What I can do is I can solve this equation for one of the variables, and then I can plug that into the area equation. Is there a variable that it would be easier to plug in for? Oh, great. So implicit differentiation is when one of the variables is a function of another variable. So for example, if the area was changed for one of the variables. So I could say that 2,800 minus 2L equals W. And I can take that and plug it in for W. And then I have a function of just one variable and I don't need to use implicit differentiation. So we have that area is length times width. And we have that the perimeter is 2L plus W. And we know that the perimeter is 2,800. And I can subtract over the 2L. And that equals W. And then I can take that and plug that in for W. So I have that the area is L times 2,800 minus 2L. And then now I have just basically a function of one variable. And to find the local maximum, I would take the first derivative and set it equal to 0. Because I have to take the first derivative, I'm going to go ahead and distribute this L so that I don't have to use the product rule. Now I can just use the power rule. So the first derivative, A prime, I get 2,800 minus 4L. So I took the derivative with respect to L. And then I can set that equal to 0. So I have 2,800 equals 4L. So I get that L equals 700. So the good news is I didn't need to use implicit differentiation because I could. So implicit differentiation is kind of when we don't have explicitly defined functions. And because of this perimeter function that I have, I was able to explicitly solve for one of the variables, and that made it a little easier. And now I have L of 700. And what I can do with that, because that represents the dimension for the length, is I can go back over here to the equation for W, and I can plug that in and I can find out what the width value is. So I have 2800 minus 2 times 700 equals W. So I get W equals 1400. And these are, we were told, we are working with meters. In fact, a maximum. What would be an easy way to do this? Well, we have the first derivative, 2800 minus 4L. If we found the second derivative, what would that be? Good. Minus 4. So what does that mean? What it means is, oh, go ahead. Very good. It means that this function's concave down everywhere. The whole thing is -4, so there's no place where it changes direction. So this is concave down everywhere, and concave down represents a local maximum. So we just confirmed that this critical point that we found was in fact a maximum. So the maximum area is when the length is 700 meters and when the width is 1400 meters. We were also asked to calculate what the area is, so we can just calculate that by plugging these in. And when we do that, we get 980,000 meters squared. So that represents the maximum area. And the dimensions are here. So typically when you're trying to optimize, meaning try to find the maximum area or the maximum profit, you're going to be working with two equations. One that you'll solve and plug into the other, and then you'll maximize one of the equations. In this case, we were told to maximize the area. So we used that we could find what the perimeter was based on how much wire we had. We solved the perimeter equation for one of the variables, and then we plugged that into the area, and that gave us a function of just one variable, and we calculated the critical point. Could we have also, instead of solving for W, right here, solved for L? Yeah, we could have solved for either one. The reason I chose W is just because if I had solved for L, I would have had to divide each term by 2, and I would have ended up with a fraction, which is completely okay. It's just the W is already completely by itself, so I chose to solve for the W rather than the L. Either way would have been completely fine. So we're going to talk about antiderivatives, and basically what they are is if I give you the derivative function, so for example, I say the derivative is 3x squared. What is the original function? So that's what we're going to do now. We're going to figure out what the original function is. Do we know the original function if the derivative is 3x squared? Very good. X to the third. One thing to note What if I had an x to the third, let's say plus 5? Could that be also a function that represents f of x if the derivative is f prime or is 3x squared? Yeah. So what happens is we could have some constant that when I took the derivative went to 0. So there's no way without giving some other information of knowing that. So what we do in cases like this is, I just chose that 5 randomly. We would write this as x to the third plus a constant. So we just say c. So the derivative of any constant goes to 0. So that's why we have to say it could have been there. We don't know. It's possible that it wasn't, but it could have been. So how did we go from 3x squared to x to the third? Well, we know when we take a derivative that we moved that 3 to the front. So I need to move that 3 back. So basically I need to move that 3 back and add 1 to the exponent. So here's what we do. Given a derivative function, we can find the original function by finding the antiderivative. Another word for antiderivative is integral. Those two mean the same thing. And this symbol here is the integral symbol. Sometimes, I believe next week, we will see the integral with some numbers. Right now, though, we are just going to have the integral. One other thing you might notice is this dx. All that the dx is saying is take the derivative, excuse me, not the derivative, sorry. Take the integral with respect to x. It's just telling you what variable you're working in. Because let's say that we had this, integrating 5, for example. Without being told, we don't really know what variable we're working with. So this dx is saying we're working with x. So we have to think, if I were to take the derivative of something and I got 5, what was that original function? We have to think going backwards. I took the derivative of something and I ended up with 5. What did I take the derivative of to get 5? Very good. 5x. So on the right side of the parentheses, if I take the derivative, I should get back to this function. Is there anything else that could have been there? Good. There could have been some constant that went to 0 when I took the derivative. So that is this rule right here. If I integrate k, so some constant k, and we just use a different letter because we already have c in other places. So if I integrate a constant, I'm going to get back to k times x, or k times whatever variable we're working with, plus a constant. Because to take the derivative of the right side, the derivative of kx would just be k, and the constant goes to 0. So what about the rule up at the top? So this rule. This is the opposite of the power rule. The power rule, okay, sorry. When we work with the power rule, we take the exponent to the front and subtract 1. But now we're going in the other direction. So instead of multiplying the exponent in the front, I'm going to divide the exponent. And I'm going to add 1 back to the exponent. Because the derivative, I'm trying to undo the derivative, and the derivative subtracted 1 from the exponent. It moved the number to the front and subtracted 1. So now I'm going to divide the number in the front and add 1 back to the exponent. There is this rule here, this part that says n cannot equal -1. Why can n not equal -1? Well, if n is -1, then that fraction out front becomes 1 over 0, and we can't have 1 over 0. So when n is -1, we have something else going on. So n cannot be -1. The power rule applies for all of the functions except for that one. So when n is -1, that's this case in the middle. It's the 1 over x function. So 1 over x to the first power. If we were to move that up to the numerator, we'd have the integral of x to the -1 dx, and we just would move it down. Thinking about derivatives, I know the answer is already here, but what do I take the derivative of to get 1 over x? Good. The natural log function. So I take the derivative of natural log and I get 1 over x. So that's why when I integrate or go in the other direction, if I start with 1 over x, I end up getting back to the natural log function because I'm going in the other direction. But now there's absolute value bars on the x. And the reason that those are there is if we're starting over here, just thinking about the derivative, if I say take the derivative of natural log x, we are working on the natural log of x domain, which means x can't be 0 because natural log of 0 doesn't exist, and it means x can't be negative numbers. So starting with natural log x, we're working on the domain of natural log x. If we start with 1 over x, though, which is what we're starting with over here, we're working on 1 over x's domain, and all that says is x can't be 0. X could be negative, though. So when we go in the other direction and end up getting natural log, we have to apply these absolute values because we have to ensure that x is positive. So that's the difference. And technically, when you write natural log x, those x's are always positive. They have to be because that's the only way natural log exists. So we just don't write them when we start with the natural log. But when we go from 1 over x to the natural log, we have to apply absolute values. Okay, so we have these 3 rules now. This is just the power rule for integration. And each one of our derivative rules that we've learned has a corresponding integration rule. So let's do some examples. Let's come back to the trigonometric integrals in a minute. So let's evaluate the integral of x squared minus the square root of x plus 2 minus x all over x. And again, the dx is just saying integrate with respect to x. And once we integrate, we've already dealt with that, so it's gone. In cases like this, we haven't worked with any any integration rules where we have a fraction, so any rational functions right now. So is there anything that I can do just using the rules that we so far have learned to find this integral? Well, the easiest thing I can recommend is to simplify as much as we can. How can we simplify? Good. So what we can do is we can write x as x to the -1, and we can, before we do that, just to separate them, is we can separate each term by the denominator, and then we can do the x to the -1. So I will go ahead and write x to the 1/2 for the square root. Anytime I see a square root, I change it to x to the 1/2 plus 2 over x minus x over x. So I just broke up each term by x. And that way, I can start simplifying. So some of these terms, they'll just simplify pretty easily. So the first term, for example, just simplifies 2x because one of them cancels. The second one, it's not a bad idea if you wanted to write this as bringing it up x to the -1. And then the last term simplifies down to 1, and you'll notice I left a little space. And here's why. 2 over x. If I write this as 2x to the -1, which I can do, I'm going to use the power rule on the first term. Once I simplify here, I'm going to use the power rule on the second term. This is just the integral of a constant. Can I use the power rule on this term? Remember, the power rule says x to the n dx equals 1 over n plus 1, x to the n plus 1, and then plus that constant. But there was one case when we couldn't use the power rule. Very good, and this is that case. So if you write it that way, it's completely fine for that third term. You just might find that you accidentally use the power rule just out of habit, and what would happen is you'd end up with 2 over 0, x to the 0, and that doesn't work. So that's why on that third term, I'm going to go ahead and leave that as 2 over x, just because that helps to remind me that that's going to be the natural log case. So what happens to the second term? What does that simplify down to? We end up getting x to the negative 1/2. So by writing it as x to the negative 1 and bringing it up, it makes it easier to simplify that second term. So let me go to the next page and just write exactly what we have. I have the integral of x minus x to the negative 1/2 plus, if it helps, you can write this as 2 times 1 over x just to help see that that is the natural log function. You could also leave it as 2 over x, and then minus 1. And I left the integral and the dx because we haven't actually integrated. We've just been simplifying so that we actually can. So we've broken apart all of the terms and then simplified, which if this fraction was reversed, we couldn't break apart a denominator, but we can always break apart numerators. So now I can use the power rule, which says x to the n being the exponent, is 1 over n plus 1, x to the n plus 1, plus a constant. We only need to put one constant, and we'll just put that one at the very end. So what is n in this first term? It's just a 1. We don't typically write x to the 1, but the exponent is a 1. So when I integrate, I get 1 over 1 plus 1, x to the 1 plus 1. So 1 over n plus 1, x to the n plus 1. And I'll simplify that to 1/2 x squared in just a minute. Then I have minus 1 over n, and in this case n is negative 1/2. So negative 1/2 plus 1, x to the negative 1/2 plus 1. And then the third term, I have 2 times 1 over x. So the 2 stays where it is, just like it would if we were taking a derivative. And the integral of 1 over x, this is where we get the natural log of the absolute value of x. And what about the minus 1? When I integrate that, what do I get? Or what did I take the derivative of to get negative 1? Very good, negative x, and now I will go ahead and add the constant that could have been there. And I do want to simplify. So the first term I get 1/2 x squared. And I can quickly check. If I take the derivative of 1/2 x squared, do I get x? Which is what we had right here. I would take the 2 to the front, which would cancel with the 1/2, and I'd subtract 1 from the exponent. Good, yes, I do. So I do end up getting the correct derivative. Over here, I have negative 1/2 plus 1 in the denominator. Negative 1/2 plus 1 is positive 1/2, so I have 1 over 1/2 x to the 1/2. And I do want to simplify the complex fraction. What is 1 over 1/2? Good, it's 2. So I will just switch that in the next step. There's nothing we can do to simplify 2 natural log absolute value of x, and there's nothing we can do to simplify minus x. Writing x to the 1/2 as x to the 1/2 rather than the square root is perfectly fine. So you can leave it as x to the 1/2. You could also switch it to a square root if you wanted to, but you don't need to. So I have 1/2 x squared minus 2 from the 1 over 1/2 x to the 1/2 plus 2 natural log x, natural log absolute value of x minus x plus a constant. And this, if I take the derivative of this, the function that after we simplified, we had x minus x to the negative 1/2 plus 2 over x minus 1. If I take the derivative of this function that we have in the parentheses, I should get back to what I had as the original integral. So if I take the derivative of that, I should get to this function, and I will. Because I would take the 2 to the front, which would cancel with the 2. I would take and subtract them from the exponent. The same thing with the second term. I would take the 1/2 to the front, which would cancel with the 2, and subtract 1. And 1/2 minus 1 puts me at negative 1/2. The derivative of 2 natural log absolute value of x is 2 over x, or the absolute value of x, which again, if we had started with this function instead, there wouldn't be an absolute value. So that's okay. And then the derivative of minus x is minus 1, and the constant would have gone to 0. So if you take the derivative of your answer, you should get back to the original question. And our original question was written a little differently, but once we simplified, this is where we got. So the answer in the box is our final answer. So let's go to trigonometric integrals for a minute. I want us to think in terms of derivatives. I know these are written above, but it kind of helps to talk them through really quickly. So what would I take the derivative of to get cosine? Thinking about derivatives, what would I take the derivative of to get cosine? Good. The derivative of sine x plus some potential constant is cosine x. So this is what I would take the derivative of, the original function, and the cosine x represents the derivative. It's just now I'm going to give us the derivative function and ask what was the original. So for me, because I've worked with derivatives for so much time, it helps me to think, what did I take the derivative of to get here? So if we were talking about the integral of sine x, what did I take the derivative of to get sine x? Well, I know the derivative of cosine is negative sine. So I wasn't asking for the derivative of, or the original function of negative sine, so all I have to do is move the negative to the other side, so I get negative cosine x. If I take the derivative of cosine x, I get negative sine. So then the negative that's already out front cancels with the other negative, and that's how I get positive sine x. And just like the other derivative values for trigonometric functions, you can always have this table around and reference it. so you don't need to memorize these. Thinking in terms of derivatives, if I took the derivative of tangent x plus a potential constant, I would get secant squared x. And then the derivative of secant x is secant x tangent x. So when I integrate secant x, tangent x, I get back to secant. If we have a cosine, let me erase this. If we have a cosine, but instead of having a just cosine x, just talking about this one right here, so k just being some sort of constant, so cosine of 3x, for example. Thinking about taking derivatives, how would I know we're integrating, but how would I take the derivative of cosine of kx? I would take the derivative of the cosine, keep the parentheses, and then multiply by the derivative of that kx, which would just be k, out at the front. So since I'm taking the integral rather than the derivative, instead of multiplying by kx out at the front, I actually am going to divide it out. So right here, that 1 over k is doing the opposite of the chain rule. Instead of multiplying by a k out front, because that's the derivative, I'm going to divide it out because I'm going in the other direction. So the integral of cosine kx is 1 over k sine of kx, and then plus a constant. And the same thing here. So that's the only difference between those. And we'll talk more about those next week. So let's do some examples. I want us to take the derivative of 2 cosine theta times 3 tangent theta plus 5 secant theta d theta. So this 2 cosine theta is being multiplied by this entire term. And unfortunately, we can't take the integral of each term separately unless they're being added together. So I can't take the integral of 2 cosine theta and then take the integral of the other terms. That's a product, and that would be a different integration technique. So the only thing I can do is try to simplify before I start integrating, kind of like I had to do with the last one. So what I can do is I can distribute this 2 cosine theta all the way through. So I have 6 cosine theta, just combine those constants, tangent theta, plus 10 cosine theta, secant theta, d theta. And in cases like this, whenever I have trigonometric functions that are a part of my integral, and right now it looks fairly complex and I don't have an integral for the way that it's written out. So is there anything that I could do to try and simplify anything further? So if we factor out cosine, so that's good. If we factor out cosine, what's going to happen is we'll end up back at the original question. Oops. But what we could do I know anything about tangent, for example? Is there another way that I could write tangent theta? So tangent theta is the same thing as sine theta over cosine theta. What about secant theta? Is there another way that I can rewrite secant theta? So secant theta is 1 over cosine theta. So these are some identities. And the benefit of doing that is if I rewrite the integral now, what is going to happen? Good. Quite a bit of our term is going to cancel. So the cosine thetas cancel out in the numerator, and in the first term, and they also cancel out in the second term. So whenever I have a question that it has sines and cosines and tangents, secants, cosecants around, I change everything that I can into sines and cosines. So the tangent I'm going to change to sine over cosine, and the same thing with any of the secants or the cosecants. I'm going to change them into sines and cosines because hopefully something will cancel. And in this case, it does. So the cosine cancels with the cosine. And then the same thing happens in the second term. So all I'm left with is 6 sine theta plus 10. So let me go to the next page. So I have the integral of 6 sine theta plus 10 d theta. And now I can integrate. So whenever I have a constant in front of, say, 6 sine theta, the 6, just like it would if we were taking the derivative, stays exactly where it is. So what is the integral of sine theta? Good, negative cosine. So I will put that negative in front of the 6. And what about 10? What does 10 become when I integrate it? Very good. Anything else? Good. So there is a constant that may have been there that when I took the derivative went to 0, so it wasn't part of our function. I believe we have one more example. Okay, we do. So our last example is find the function f of x such that the derivative, which is given to us, is 5x squared plus 3x minus 10. And then they say with f of 1 equals 2. This information is telling us some information about the function so that we can find out what the constant is. So this is used to find the constant. So that we will use later. So they gave us the derivative function. They said the derivative is 5x squared plus 3x minus 10. And they're asking us to find f of x. How am I going to go from the derivative to the original function? Good. I'm going to integrate. So if I integrate f prime of x dx, just saying with respect to x, that will get me to the original function. So I'm integrating 5x squared plus 3x minus 10 dx. So I can use the power rule, on the first two terms, and the last term is just integrating a constant, so I'll end up with negative 10x. So in the first term, I have 5 over 2 plus 1, x to the 2 plus 1. You don't necessarily have to write that step. I'm mostly just writing it for our notes. And then I have 3 over, and what is the exponent in that second term? It's a 1. Again, we don't write it, but it's a 1. So I have 3 over 1 plus 1. And then minus 10x. But there is a potential constant. So again, you could have gone right to 5 over 3x to the third plus 3 over 2x squared, and then minus 10x if you wanted to. I just wanted to write out the steps so that we know where they came from. So we have 5 over 3x to the third plus 3 halves x squared minus 10x plus a constant. So once we integrated, we got 5 over 3 x to the third plus 3 over 2 x squared minus 10x plus some potential constant. What does this represent? Well, we were told the derivative function, and then we integrated. Good, the original function, so f of x. If you wanted to quickly just check, you don't have to, but just if you want to make sure that you didn't make any mistakes with your integration, we could take the derivative quickly. So 3 out to the front, subtract 1 from the exponent, so we get 5x squared. Same thing here, take the 2 to the front, times 3 halves, it stays where it is, subtract 1 from the exponent, those 2's cancel. And then minus 10, so we have 5x squared plus 3x minus 10. So we did end up getting the correct derivative. We didn't need to check. I just wanted to show that we can always take the derivative of our answer and make sure it's the same. So we were also told that f of 1 equals 2. So what that means is if we plug in x equals 1, that function is going to equal 2. And that means our only unknown at that point would be the constant. So f of 1 equals 2. So 2 equals 5 over 3 times 1 to the third. I'm plugging in 1 for all of the x's. Plus 3 over 2 times 1 squared. Minus 10 times 1 plus the constant. So now the constant is the only thing that I don't know, and I can solve for it. So this information, again, was used to find the constant. So I have 2 equals 5 over 3 plus 3 over 2 minus 10 plus the constant. And all of this, if we simplify, is negative 41 over 6. So to solve for the constant, I just need to add that over to the other side. So I have 2 plus 41 over 6, when I add that over to the left, equals the constant. So that we get that the constant is 53 over 6. And we can take that constant and plug it back in there, and that will give us what the original function is. So, putting this all together, our original function, f of x, is 5 over 3 x to the third plus 3 over 2 x squared minus 10x, and now we know that the constant is 53 over 6. So the only way that we can figure out what the constant is if we're given some sort of extra information. So in this case, we were given f of 1 equals 2. That's the only way we can find out what it is. Had we not been given that, we would have just had to leave it as right here.